Okay, I very quickly wanted to go through the Hazelrigg practical and relate that back to the Trembeth diagram that you would have seen in the lectures. So if you remember that kind of image in a very summarized kind of way, we have our surface, we have our atmosphere, and then we have space up here. Okay, and what we're interested in calculating is the amount of energy which comes in from the sun at the top of the atmosphere, E in, if you like, the amount of that energy which reaches the surface, so I'll call that shortwave surf here, and of course that's not going to be the same as E in, it's going to be less because some of this sunlight coming in is reflected out by clouds, some of it's going to be reflected by the surface, and some of it's going to be absorbed by the atmosphere. Okay, so let's just think about this for a minute. E in is going to be a, because we're not talking about the whole world, we're talking about a location on the sphere. So this is going to be a function of latitude, time of year, and time of day. Okay, so that's going to be our energy in, and that's the calculation you go through on the first part of the worksheet of the Hazelrigg worksheet. And so what you do is I ask you to calculate energy in. It comes in watts per meter squared for 9, 12, and 3. It gives you 3 values. In fact, 9 and 12 are the same, which in reality will be connected up with a nice smooth cosine curve. And what you would do is calculate the area under this curve between 3 and 9, because we're interested in the total amount of energy, the integrated energy over this 6-hour period. Now you can do this exactly, solve the integral for the cosine. It's a little bit complicated. I go through it on the spreadsheet and a bit on the Moodle. Or you can just estimate it by assuming we have a triangle here on top of a rectangle. Okay, now this has units of hours and we're doing it over 6 hours here. This has units of watts per meter squared. So the area under here, we say that has unit of watt hours per meter squared. And you'll see that in the Hazelrigg sheet. This actually is very basically equivalent to joules if we multiply it by another factor, 3,600 joules per meter squared, because watts is joules per second, and here we're timesing watts by hours. In any case, the area under this curve is roughly 3,000 watt hours per meter squared, more or less for any time of the week that you did this. Okay, let's come back here. So we've got our energy in, which is not using any of the apparatus at Hazelrigg. It's just doing some maths calculations, which all relate back to trigonometry. But here we're interested in the amount of shortwave radiation which reaches the surface. And this is going to be less than energy in because of the amount which is reflected by the surface and by clouds and absorbed by the atmosphere. Okay, and we have 3 different ways of estimating this. We have a solarimeter, which is our most believable estimate. So this is the digital estimates. This is the one that we're probably going to rely on in our calculations. But we also have another couple of ways of estimating it, and we just throw that in there just to show that there's more ways to skin a cat, essentially. So one of these ways is the Gunbalani solar integrator, which has a copper black ball which only absorbs solar radiation, and as this heats up it causes alcohol to evaporate down a burette, which you measure down here, and the level of the amount of alcohol that's distilled over, say, the 6-hour period will be proportional to the amount of solar energy which is received at the surface. Okay, so this is the GB, the Gunbalani. And then similarly, there's an evaporation pan where you measure the liquid level at both at 9 and at 3, or maybe 9, 12, and 3, and measure how much is evaporated, and the amount of liquid which is evaporated is also proportional to the amount of solar energy absorbed. With the evaporation pan, of course, it's not just the the liquid evaporating, there might well be some precipitation. So that's why we need to account for anything that would add to the evaporation pan before we actually calculate the amount that's evaporated. All right, so for these guys here, you'll get a value, let's say maybe you get a value of energy in watts per meter squared at 9, 12, and at 3, and maybe it looks a little bit like this after you've gone through the calculations, that is, and then you need to just calculate the area under this curve. Okay, let's think about the long wave part of it. So this is short wave or solar, which is peaks in the visible. Now we want to think about long wave or terrestrial radiation, which peaks in the infrared. Now here we're going to be interested in the atmosphere, clouds, and the greenhouse effect. So the surface will emit long wave radiation, and we'll get some long wave radiation back from the clouds and back from the atmosphere. This is the greenhouse effect, GHG, greenhouse gases. So this is pretty easy. We can estimate the outgoing long wave radiation from knowing the temperature of the surface. And in fact, we use the 5 centimeter soil temperature here. And if you remember from the lectures, this energy equals the radiative energy is sigma T to the 4. Well, this is our, I'll just put an S there for our surface temperature. Sorry, sigma T to the 4, get my writing right. This is the amount of energy which is coming out from the surface is proportional to the temperature. So the temperature of the surface to the power 4 multiplied by the Stefan-Boltzmann constant. Now similarly, we can do this for the atmosphere, the energy that's coming back down. So here's our upwelling long wave. This is our downwelling long wave. We just need to know what the temperature of the atmosphere is. Now we can estimate that by thinking about how the temperature changes with height in the atmosphere. So this is height in the atmosphere, this is temperature. We can assume that the temperature decreases at a constant rate. This is the lapse rate. And the standard atmosphere, which is a construct really, but something that we use here, we can assume that the temperature drops by 7 Kelvin per kilometer. Okay, and then for a set of arguments, we want to know how far up in the atmosphere do we need to go. What's the relevant temperature for us for emitting energy down to the surface? If we go up too high, then the energy which is coming down from here, it will all be absorbed by the atmosphere before it reaches the surface. This relates to something called the optical depth. And so, long story short, we go up to 400 meters. Okay, and that's the temperature we assume for the temperature of the atmosphere. So you'll see in the worksheet, temperature of the atmosphere equals temperature of the surface minus basically 0.4 times 7, which is 2.4. Okay, so that's 400 meters. If it was a full kilometer, it would just be minus 7, but it's not a full kilometer, it's just 400 meters. Okay, and so once we know that, we can also do the energy that's coming from the atmosphere due to the greenhouse effect, and that's similarly, that's sigma T to the 4. But here we also added an extra term called the emissivity. And this says that the atmosphere is not emitting at all wavelengths. It's not a perfect black body. It's only emitting at some. So we adjust it right. So if it was emitting at all wavelengths, this would just be 1. But here we know it's not emitting at all wavelengths, so we adjust it down. So this epsilon alpha factor is actually 0.75. We're also interested in the amount of energy coming down from clouds as well, which we add to this long wave. This is long wave downwelling energy, and so we do this in a very similar way here. We need to know the temperature of the clouds, and so we estimate the temperature of the clouds by estimating the base height of the clouds, and we use the same adjustment here. So the temperature of the clouds, Tc, the temperature at the surface minus 7 times the cloud height in kilometers. Okay, and then we can do something like this. We can take it, so the energy from the clouds is going to be sigma Tc to the 4. But here we also multiply it by the cloud fraction, which we call B in here. So if the sky is completely covered in clouds, then this would be 1. But if it's not, so if it's 0, if there are no clouds, then obviously this term is 0. And then we also account for the fact that we're accounting for some of this energy already coming from the greenhouse effect. So we essentially say 1 minus this number. So this is actually 0.75. So we add in the extra energy which is not coming from the atmosphere by saying 1 minus epsilon alpha. And this is because clouds emit across all wavelengths, but we don't want to add to the wavelengths that are already there. So we adjust it like this. So sorry, it's a very long-winded way of saying essentially the clouds are adding to the energy which is coming from here, recognizing the fact that they emit across all wavelengths. So you'll see in the worksheet, we add this to this. There's an extra epsilon term, but let's not worry about that too much. And this gives us our downwelling long wave. Okay, so upwelling long wave is pretty straightforward. Downwelling long wave is a little more complicated because we have to think about clouds and the greenhouse effect. But basically, they're all still relating to this sigma t to the 4 term. And then back over here, this is just a function of geometry, really. And then here we can actually have direct measurements from the solarimeter, which we can compare to our estimates from here. Okay, so let's put all those numbers together. Numbers that I've calculated for Friday the 16th. So the energy coming in at the top of the atmosphere over that day is 3,148 watt hours per meter squared. The energy of that solar energy which reaches the surface, that's 2,307 watt hours per meter squared, which means that it's reflected by the surface and by clouds and absorbed by the atmosphere. Altogether, that is 841 watt hours per meter squared, which is 27% of the energy at the top of the atmosphere. So we're saying that of the energy at the top of the atmosphere, 27% of it is either reflected by clouds, by the surface, or absorbed by the ozone layer or by a small number of other constituents in the atmosphere. If you compare this to the 30% of the global average albedo, plus maybe another 15-20% for absorption, that's actually is a bit lower. Obviously, this is just for a particular day, and it happened to actually be a day which there wasn't an awful lot of cloud cover. Okay, so that's our solar side of things. Outgoing long wave from the surface is 2,080 watt hours per meter squared, and then the energy which is coming back from the atmosphere is 1838 watt hours per meter squared. Okay, so these are all of our summary numbers, but what we're missing is our estimate of the non-radiative fluxes. Okay, so what's left? What's left to come out here? So sensible heat and latent heat. So we can infer that from an energy balance from the surface. So the surface is receiving 2,307 watt hours in the short wave, plus 1838 watt hours per meter squared in the long wave, which gives us 4,145 watt hours per meter squared. Total down to the surface, so down to the surface. The surface, though, is only emitting in radiative fluxes 2,080. So we can do 4,145 minus 2080, which gives us the balance of the energy which we're missing here, and that is 2,065 watt hours per meter squared. So the value of this is 2,065 watt hours per meter squared for our non-radiative fluxes, and these are sensible heat, so basically conduction from a hotter to a colder area, latent heat, transfer from converting liquid water to gaseous water or water vapor, And also there will be a term to the ground as well when we're considering a local energy balance such as this. There may also be a term if, say, a warm air blew in over Hazelrigg over this day, so air that was not warmed by this energy here, then that would actually count as like an extra term in this radiative budget, which would in this energy budget, sorry, which would be counted here in these this non-radiative term. Okay, so that's how the balance works out. Everything is set out like this on the spreadsheet for you to see how I did the calculation. Good luck.